Next, we're going to talk about how we can include ARIMA models with ARCH models. So previously, we've defined these ARCH models as follows. Let's say we have one of order m. Y sub t is equal to sigma t times epsilon sub t, where the sigma t squared then is this linear combination of these alpha parameters with these past y values that are squared, and epsilon is distributed independent. Normal distribution means 0, variance 1, where the normal distribution there is used for estimation. Now we do have conditions on these corresponding parameters as well. Now to incorporate ARIMA models in the situation, suppose we observe some time series called x of t. With an ARIMA model, of course, we could have an AR component, we could have differencing, we could have an MA component, and then what W sub t is our white noise. And again, for estimation purposes, we would typically assume that had a normal distribution. Now in this particular setting though, we're going to also incorporate that ARCH model. So rather than this being purely white noise, we're going to have sigma squared sub t as my variance, where the sigma squared of t is this linear combination of the alphas with these past corresponding values of y squared. Now with these past values of y squared, note that there is a small typo here. This should be t minus m. And what these y's then represent in this particular setting is essentially the residuals from an ARIMA model fit. I guess I could have used some other notation, but I chose to use y sub t here since that's how we were using it above. And so this is going to help take care of the non-stationarity and the variance that can occur when you're working with ARIMA models. So then this comes into a situation, well, how would I decide between the different kinds of models to use in this situation? So we can talk about model building briefly. And what one could do is build an ARIMA model for the observed time series to remove any autocorrelation that is in our x of t. Refer to the residuals then as y sub t. Then we look at these squared residuals. We look at the ACF, we look at the PCF to make a decision of, okay, now do I need to now count for the variance changing through time? And if so, we can use the PACF plot to help us guide us to choose a particular order for our AR model. Then we estimate the model with both the ARIMA part and the ARCH part all together. We use maximum likelihood estimation, and then we look at the final residuals that we get from the model to make sure that everything looks okay. So let's take a look at an example. This example again comes from Shumway and Stouffer's book. What they were doing is modeling the gross national product, or GNP. They have quarterly values associated with this time series, and they suggest that an AR1 model to the first differenced log transform data was something that would be good to use, and then to examine an ARCH model on top of that. We will estimate both the AR1 part of the model and the ARCH model simultaneously using the GARCH fit function. UGARCH fit will also work. So let's let x of t be GNP at time t, and this is what we get. Again, we have quarterly data, and we can go ahead and put, let's say, these GNP values into an object called x. Please note that this GNP data set is actually in the ASTSA package provided by Shumway and Stouffer. So if we look at a plot of the data over time, what we see here is that we do have this linear trend indicating we have non-stationarity with respect to the mean. So let's take a look at a plot of the first differences to see if that helps us out. And indeed it does. Now, from looking at this plot here, we can see that maybe the variability for this part of the time series is different from the variability in that part of the time series. So perhaps we do have non-stationarity in the variance, indicating that we need to fix this. And so rather than going directly then to using ARCH models, what Shumway and Stouffer decided to do was work with the log transformation and see with the first differences and see, let me start over. They decided to work with the log transformation of these first differences. And we've seen this kind of thing done before. So the log of x of t minus the log of x of t minus 1. This kind of ends up being like the log of a return in an investment, although obviously here GNP is not an investment. Now, because I would like to actually replicate their example as is, I chose not to pursue anything else further here with respect to what we're working with here. Do note that perhaps I shouldn't call this y sub t, maybe something else, because we're going to be using y sub t later. But there are definitely other avenues here to explore with respect to this analysis. So for example, one could look at a plot of these log of the first differences. Look at excuse me, look at the first differences for the log of x of t and see if that nicely handled the problem here. You know, just from looking at this plot here, well, yes, I do have a little bit concern about the differences in the variability, but I could see, for example, maybe everything was still okay with this particular plot. So let's go ahead and estimate then the autoregressive 1 model with respect to this data. So what I'm going to do is use the diff function here, where I'm going to take the log of x of t and find the first differences. Put that in an object called GNP GR. Then I'm going to fit a model directly to these first differences of the log. And so the order of my model is not 1, 1, 0, but rather 1, 0, 0, because I've done the first differences before. Now, why did I do that? This is the approach that Shumway and Stouffer did. I'll come back to this, a discussion about this shortly, to give some reasoning for why they decided to do the differences outside of the ARIMA function. But for now, let's just duplicate what they did. Also, I have include.mean equal true here. What that's going to actually allow us to do is estimate a drift term too. Put the results into mod.fit.ar. So here's information about the model's fit. So for example, here is phi hat 1. Now, let's look at some diagnostics associated with this particular model. So I use examine.mod.r. I use the corresponding function in there to do these diagnostics. And this is what I get. Look at my standardized residuals. They seem to be pretty good. We do have one that's outside of 3 there, but otherwise things look to be pretty good. Maybe a few here too. We can then look at ACF plot of the corresponding residuals. Again, lag 0. We don't look at. And what we can see here with this ACF plot, we have really no significant autocorrelations. So perhaps just this AR1 model is good enough. Look at the Jung-Box-Pierce test. We have relatively larger p-values for all lags, so that's good as well. PACF plot of the residuals. Again, no significant partial autocorrelations. Here's my histogram of my residuals. Maybe we have a little bit of deviation from normality. Definitely from the QQ plot, we see maybe, let's say, fatter tails than what we would normally expect if the normal distribution was completely satisfied. And so this is then the model that we get from estimating this corresponding data here. now what we need to do, or I'm sorry, before we get to the next step, let me mention that I could have also estimated the models as follows. So what I could have done, actually that's incorrect there. I could have put, didn't write that very well, log of x right there. I could have estimated the model with the ARIMA, log of x. Here's p, here's d, here's q. To get that other term there, I could have also get that drift term. I could also get that value there too. Now, however, though, once we estimate both the ARIMA part of the model and the ARCH part of the model using one of these functions, we're going to find that we don't have a way to specify d in these particular functions. So we will always have to do the first differences outside of the function first to actually estimate the model that we want to. To be honest, I find that disappointing that these kinds of functions are set up like this, and towards the end of the notes I will speculate on why I think these functions are set up like this. Okay, so now with the models fit, let's get the residuals out. I'm going to put them into what I call y sub t, or y in terms of our syntax here. So I'm going to put them into y. Then I'm going to do an ACF and PCF plot of y squared. And this is what we get. So we have some borderline significant values in the ACF and the PACF plot. And again, I want to emphasize that these are rather borderline. If I saw something like this, I would not necessarily immediately jump to using an ARCH model. After all, we are already using this log transformation at the beginning. Maybe that was enough to handle this potential non-constant variance that we have. And again, it was even questionable if we had non-constant variance. So, well, what does Shumway and Stouffer say for their particular example? They said it appears there may be some dependence left in the residuals. And because of that, they decided to go ahead and work with the ARCH model too. And I say here, well, yeah, maybe there is, but I could definitely justify not going to an ARCH model in this situation. But let's go ahead and do that. Let's try an ARCH1 model, because we have a moderately significant value there, and see what happens. So I'm going to use the GARCH fit function, and this is how I can do it. So GARCH fit, formula equal. Now this is where I can specify the two different kinds of models. I'm going to specify an ARIMA-10, in other words AR1. And then also I'm going to specify a GARCH-10, in other words an ARCH1 model. And I'm going to do it with that transformed data. And this is what I get. I summarize the models fit. Here are the corresponding estimates. So here's phi hat 1, for example. Here is alpha hat 1. Now notice if I were to do a hypothesis test of is alpha 1 equal to 0 or not, we have a marginally significant result. To be honest, I'm not surprised to see this, because again, that PACF plot had a marginally significant value there for that lag 1. And also it was even questionable to begin with if we do truly have non-constant variance, where we have non-stationarity in the variance. With respect to the Jung box tests with the residuals, notice what we get here. For just the regular residuals, we have everything's okay, but for the squared residuals, hey, there might be some significant values out there. That's kind of interesting. Also, what's interesting is that the authors do not choose to explore this further. Also, the authors indicate, yeah, there might be some evidence against non-normality, some evidence of non-normality, but again, they don't explore it further. Here's then the corresponding QQ plot where we see what would be on the tails of the distribution. We have some evidence against normality. So though, based upon this output though, this is how we can go ahead and specify the corresponding model as well. So the purpose of this example was try to reproduce the results that were in Shumway and Stouffer's example. And my parameter estimates, everything else matches what they got. Am I satisfied with the model's fit? No. There could be other investigations done corresponding to this data as well to see if maybe you can get a better model's fit. But again, the purpose here was to illustrate the idea of how to estimate both an ARIMA and an ARCH model simultaneously, and that's what I did here. On your own, if you're interested, you could explore this data further to see if you can get a better model. Now this last note here is, well, why doesn't GARCH fit or UGARCH fit allow for the value of D? Here's my speculation about what the reason is. These GARCH models are used a lot with financial time series. With a financial time series, actually understanding the value of, let's say, one share of a stock or one unit of some other kind of financial instrument is often not as important as understanding the return from one period to the next of that financial instrument, such as you have a 2% increase in the stock price over time. And if you looked at the return, let's call it R sub t, essentially those first differences are built in already. So if this is truly what you want, you don't need to do further first differences, and you can just interpret that R sub t itself and model that R sub t itself, and you're done. Now, of course, in this particular example, GNP is not a type of investment. It's a measurement of the economy of a particular country, typically. And so, you know, maybe in this case it would be of interest to incorporate D into these kinds of functions, but unfortunately it's not there automatically. Okay, so this is a real brief introduction of how to work with ARIMA models and ARCH models all at the same time.